Hello. This time around, we are going to look at another topic that has to do with factors that affect the electrical resistance of a metallic conductor in a given circuit. Now, there are four factors that affect the electrical resistance of a metallic conductor in a given circuit. And these factors are, these factors are number one is length of the conductor. Okay, number one is length of the conductor. Length of the conductor. That's number one factor that affects length of the conductor. Okay. All right. So number two is the cross-sectional area of the conductor. Number two is area of the conductor. Area of the conductor. Conductor. That is A, capital A, right? Number three, the third factor that affects the electrical resistance of a metallic conductor is the temperature of the conductor. Temperature, okay? Temperature, that is T, right? And then the fourth factor that affects the electrical resistance of a metallic conductor in a given circuit is the nature of the material. The nature of the material used, okay? The nature of the material used, okay? The nature of the material used in constructing the conductor, okay? In the making of the conductor, the nature of the material is very, very important. So these are the four factors that affect the electrical resistance of any metallic conductor in a given circuit. Now, we are going to take time to analyze how each of these factors affects the resistance of a metallic conductor. All right, so we begin with the length of the conductor, okay? We begin with number one, length of the conductor. So, length of the conductor, that is L. Now, the resistance of a conductor with a uniform cross-sectional area is directly proportional to its length. So we put it this way, it's directly proportional to its length. What this means is this. If, for instance, the length of the conductor is just 2 cm, it means that the conductor in question offers 2 ohms as the amount of resistance to the circuit. That means it offers just 2 ohms. If the length of the conductor is 5 cm or 5 meters, it means it offers 5 ohms to the circuit as resistance to the circuit. So that's what it means. If the length of the conductor is reduced, also the resistance it offers is affected. All right, so that is about the length. Then number two is the area. The area of the conductor, in other words, the cross-sectional area of the conductor also affects the resistance of the conductor. How? If the area of the conductor is large, the resistance it offers will be very, very small. But if the cross-sectional area of the conductor is very, very small, it offers a large amount of resistance, and vice versa. That is it. Okay, so we represent that with R is inversely proportional to the area of the conductor. Okay, that's what it means. That's what it means. The resistance of a metallic conductor with a uniform cross-sectional area is inversely proportional to its area. That is it. Okay, and it has been represented mathematically as force, as you can see on the board. Now the third one is temperature. Temperature. Temperature T, capital T, okay? Temperature here The resistance of a metallic conductor is directly proportional to its temperature. What it means is that as the temperature increases, resistance of such a conductor also increases. As the temperature decreases, resistance of such a conductor also decreases. That is it. So we represent that mathematically as follows. R is directly proportional to T. Alright? But materials such as carbon does not obey this, because at a certain constant temperature, the resistance of carbon tends to decrease. As the temperature varies, the resistance of carbon decreases, and vice versa. So carbon cannot be used as one of the ohmic conductors or metallic conductors. So we don't apply carbon certain things here. There are also some other materials that are not affected so much by the variation of temperature, and such materials are constantine and manganese. They maintain stable nature under certain amount of temperature variation, and that is why such materials are used for standard resistors that can be found in our various labs. So, having said that, the resistance of a metallic conductor is related to its length and the cross-sectional area by this general relation, given as R is directly proportional to length and inversely proportional to its cross-sectional area. All right. Now, if we introduce an equality sign to change this proportionality sign to equality sign and a constant, simultaneously we have R is equal to rho all over A. Okay? Where R is the resistance of the metallic conductor, rho is a Greek word being used as a constant here, or constant of proportionality. Then L is the length of the conductor being discussed, and then A is the cross-sectional area of the conductor under piston. Now, we have said that. We can use this mathematical expression to solve any kind of question emanating from factors affecting metallic conductor. We can also find the resistivity, okay? The rho there represents the resistivity of the material, R, okay? We say, okay, rho represents the proportionality constant, all right? It represents proportionality constant, known as the resistivity, okay? Resistivity of the material, okay? So the Greek word rho, I repeat, is known as the proportionality constant. But this proportionality constant represents resistivity of the material. All right, the fourth one we are going to look at quickly is nature of the material. Of course, certain materials, that's number 4. The fourth one is nature of the materials, okay? Okay? All right. The resistance of a metallic conductor also depends largely on the kind of material that is used in the construction of the metallic conductor. So, materials such as copper, okay? Materials such as copper, all right? Silver, and the aluminium. Materials such as copper, silver, and aluminum to a very large extent can be accepted, okay, in the construction of a metallic conductor because of their fine resistance, they offer in an electric circuit. All right, so having said that, but we use copper mostly because copper is less expensive than silver and aluminum. So most times you see certain electrical appliances have their various contacts with, made of copper materials and so on and so forth, because it is less expensive and cheap. I mean, very cheap to find. All right, so that is why copper is mostly used in such arrangements.